Okay, good day, students. Today we will be covering a beam to take us back to N2 to ensure that we know how to do our moments. So, in the presentations I've sent you previously, we have three states of equilibrium. We have, let us put it here, type three states of equilibrium. So, with the three states of equilibrium, we will be using these three throughout all our moments from bending moments to shear force to bending moments as well. So that is the sum of the forces upwards equals sum of the forces downwards. That's a state of equilibrium. And then we have sum of the forces clockwise equals sum of the forces anti-clockwise. And then we have sum of the forces to the right equals sum of the forces to the left. So this is our bread and butter when it comes to solving these guys. So this is a simple one, just to get us nice and warm, and then we will do another more complex one. So okay, so right here we can ask you three questions already. We can ask you to calculate RL, RR, and then also to balance the beam. To balance the beam, we will be using this one, but we will get back to that one. We'll get back there. So okay, so step one. Step one. Let us get RL. Okay, so to find RL, we will be taking, to find RL, we will take moments around or about RR. So that would look like sum of the forces clockwise equals sum of the forces anti-clockwise. So now we need to, once we have stated our formula, we have a mark already. So now because we're moving about there, about RR, make as if though we are standing at RR and we are looking at the forces come about towards us. So now we know RR is pushing up, RR is pushing that way. We know our 8 kilonewtons is pushing this way. Um, we know that our 10 kilonewtons is pushing this way with reference to that point there. And then we also have a UDL. A UDL is a uniformly distributed load. So 4 kilonewtons per meter across 5 meters. So it's 4 across each of the meters to make 5 meters. So 4 times 5, it gives us in the very center, a point load. Now, let's change the color to be a red. To give us a point load of 4 times 5, which gives us 20 kilonewtons. So 20 kilonewtons point load for that UDL there, in the center. Okay, so let us tackle it now. Let us substitute now. Now we're going to substitute now. So we want all the clockwise first. Let's just do the clockwise. So we want all the clockwise. So we know this one is clockwise. We know that one is clockwise with reference to here. And then the 8 kilonewtons is clockwise as well with reference to this one here. The 10 kilonewtons is going anti-clockwise. This point load here by the UDL, this 20 is also going anti-clockwise with reference to this point. Okay, now we substitute. So now we can say, okay, let us change to black. Now we can say RL in a bracket times. So now, what is moments? Okay, so let that be on top. So moments is force times perpendicular distance. This is moments. We are calculating moments. Moments here. So what that is force. So RL is the force times the perpendicular distance times the perpendicular distance to the reference point. Our reference point is RR, which makes it RL is the force and the perpendicular distance is 8. So 5 plus 3 gives you 8 meters. Just like that. And then we add this because we have another 8. We have a force of 8 times his perpendicular distance. His perpendicular distance is acted at the distance of 2 meters. So 2 meters. So 8 times 2 meters. So 8 kilonewtons times 2 meters. Okay, and that concludes the clockwise calculations for that one there. So now we can move over to the anti-clockwise. So anti-clockwise, we have, okay, let's start with our furthest point. So yeah, we got our 20. So, but let's break it down. Let's remember all our steps. We have a UDL here. So it's 4 times, so it's 4 kilonewtons, 4 kilonewtons across 5 meters. Yeah? So it's 4 for every meter, 4 kilonewtons for every meter across 5 meters. So it's 4 times 5, giving us that 20. Yeah? Giving us that 20 kilonewtons in total. But anyway, so now this is the force. Yeah? This is force. This would be force now. So this is now force. Now we must times our perpendicular distance now. So now times our perpendicular distance. So here our UDL point load will be centered in the middle of that 5 meters. So now we've got 2.5 this way and 2.5 meters this way up until this point. So we got 2.5 plus 3 meter to the reference point. So 2.5 plus 3 meter gives you a 5.5. A 5.5. And that is that one. Now we're gonna add our second and last anti-clockwise calculation. We have a 10 kilonewtons force, so 10 kilonewtons times a perpendicular distance of 3 meter to the reference point. And that is the way we do it. Okay, now we simplify. Simplify, we want RL alone now. Okay, okay, let's do all the steps. Let's do all the steps. So RL times 8. So this one is going to go over, and when this goes over, it's going to be subtract. So okay, here we've got 20 times 5.5 plus this bracket here, 10 times 3, and then we're going to minus, because now this is plus, when it goes over the equation sign, it's going to be minus, so minus 8 times 2. And then what we do is, because we want this one alone, we can say now divide by 8, and then divide by 8. And we leave RL equals. Now we punch this whole thing into the calculator as it is. That's gonna be okay in brackets. Now we keep all our brackets 20 times 5.5 plus bracket 10 times 3 minus bracket 8 times 2. That is divided by 8. And then we are left with a 15.5. So 15.5 kilo newtons. Okay. So now we want to find question 2. We now want to find RR. Okay. And then now to find RR, we do the same steps. Same process. But let us maybe just redraw quickly this beam here so we can reevaluate for RR with the same processes. Now we've redrawn our same beam once again, but now it go a bit flipped. So now we will be looking at RL as a reference point now to find RR. So we want to find RR now. So now we will use RL as a reference. So we would be standing here in the reference and seeing how all our forces are acting towards us standing over there. So let's begin with R because we're looking for RR. So now we're standing there. We are going to be looking like that, and then that's just going anti-clockwise. Yeah, it's looking like the only one going anti-clockwise because now that's 8 kilo newtons is going clockwise. That's 10 kilonewtons is going clockwise. This 4 times 5 UDL giving a point load of 20 kilonewtons in the center of that 5, 2.5 meters this way, 2.5 meters this way. So now this 20 kilonewtons point load is going anti-clockwise as well. So now what do we do now? We are going to state our formula from our equilibrium now. So now we will use the same as we did here with our second state of equilibrium. So some of the forces, and I like to begin with the reference, first. So you can either have clockwise or anti-clockwise first, but then the opposite must be true for your next equation. So we want and we know R will be going anti-clockwise. So now we can set some of the forces anti-clockwise equals sum of the forces clockwise. So now what we can do is just bring our going up the side. Okay. So now we substitute. So now what we say is R times the perpendicular distance now. So perpendicular distance would now be from R to the new reference point plus 3 meter plus 5 meter to the reference point of RL. So now that is RR times 8 meters. Okay, and then there's no other anti-clockwise equations. So now we can move right over to our clockwise calculations. Okay, so let's go. Let's do this one. So we got now. Let's begin at this point now, just to shake things up a bit. Because it will all be the same if we start here, there, here, but we must just account for each of the forces in play. So now we got 8 kilonewtons. So that's the force, no? Because we know moments is a force times perpendicular distance. So now this is the force times perpendicular distance. So perpendicular distance from 2 meters plus 3 meter plus 5 meters, all to the reference point of RL. So that is 5 plus 3 plus 2 gives us 10. So 8 times 10 meters. Finished. Next one. Now we got the next one. You see there's 10 kilonewtons standing here. Okay? Perpendicular distance, we know is going clockwise. It's going clockwise. So now we say from this 10 kilonewtons to the reference point is 5 meters. So now we state that. So we know it's a force of 10 kilonewtons times its perpendicular distance of 5 meters. Finished. To the next one now. So now we know this is UDL. Let's break this down one more time. Break it One more time down. So we've got the 4 kilonewtons per meter across 5 meters. And that gives us that 20 kilonewtons point load, right? Yeah? That is the force. Yeah? This is force. Now we need 2 times the perpendicular distance. And the perpendicular distance is coming from the center point of this 5 meters. Yeah? 2.5 this way, 2.5 this way. So it's from here to the reference point. That is 2.5 meters. So now 20 or 4 times 5 force times perpendicular distance of 2.5 meters. And then what do we do now? Simplify. All of our equations are complete. Now we can move straight over to simplifying. This would be 8 r because it's like a variable. And then we just substitute this whole thing here. We can put this in a calculator directly. Let's just punch it in together. Okay, so here we got 8 times 10 plus 10 times 5. Let's just keep all the brackets in there so everything is lekker and lovely. So then we got our 4 times 5 times 2.5. And then we're left with 180. So 180. Yeah? So now we want to get R alone. So divided by 8, divided by 8, divided by 8 that side. And what you do on this side, you do on the other side, alright? Okay, so now we are left with R, and then we say 180 divided by 80 divided by 8 is giving us a 22.5 kilonewtons. Please remember our unit of measurements, please, guys. Okay, now that we have found with the size. So now that we have found RL, we have found RR. Yeah? We have found them. Yeah? So what is next? Now we balance now. Now we balance, we make sure that we are correct in our calculations now. This is how we verify our marks. Yeah? Yeah, there's enough space here at the bottom. Let's do it over here. Okay, so number 3. Now we balance our beam. Okay, so we know that our RL and our RR is calculated. It's right there. Ne? So now we will go to our state of equilibrium. Now we will select one. Now we will select one and we will select this one here. It's the only one that we can select given our forces on the beam now. Okay? Up and down vertical forces. So we know. Let's just read out our formula now. So here we've got sum of the forces going up equals sum of the forces going down. Okay? So up we've got RL. Yeah? RL is pushing up. RR is pushing up. And there's the only 2 forces pushing up. So we will substitute now and say RL is 15.5 and then RR is 22.5. Okay? That make sure I can see there. Yeah. Okay. Finished. So now we go over to the next now. The next forces now. So the next forces would be our UDL. Okay? Point load pointing down. So we've got 20 kilonewtons pointing down. Then we've got a 10 kilonewtons pointing down as well. Pointing down, we've got 10. And then one more, we've got 8 kilonewtons pointing down. And now we substitute that into our formula as is. Okay, so now we've got 20 plus 10, plus an 8. Okay, so now we equate both of these. We equate both of these now. So we say now, we say 14.5, yeah, plus 22.5. And that's giving us a 38. A 38 kilonewtons. Yeah? And then we've got the other side now. So 20 plus 10 plus 8 is giving us a 38 kilonewtons. Beautiful, balanced. Now we say, therefore, beam is in equilibrium. Equilibrium. And there we go. There we have it, guys. Just like that. And this is the process we will use for all the beams. So sometimes, because of decimal places, when it comes to rounding off, round off as little times as you can. So I'd say, for the most part, 4 decimal places. If you're still at the stage here, 4 decimal places, just for that more accuracy. Because the time you get here, you must balance your beam. You will be a few decimals off. Then I'd say round off, make magic, but don't be too far out, because I will be checking how accurate you are. So I can see how far you've rounded off here. If you round it off too soon, too much, I will able to tell that. But yeah, this is bending moments. Not bending moments. This is moments, guys. Then the bending moments and shear force. There's another video already. On YouTube. But those I just gave us for background knowledge on moments, for those who don't know, and for those who are a bit unshaken on that matter. I'll make another video breaking up with oblique forces, with sine and cos, just for everybody's clarity. But yeah, thank you so much for watching, guys.